Hi, this is a video going through as much as I can about OCR GCSE Computer Science Paper 1 in half an hour. This is not a substitute for more thorough revision. Of course, if you've got more than half an hour, please go away, look at my other videos. There'll be a playlist below, which is specific to OCR. Do other stuff, but if you're right before your exam, hopefully this will be useful for some last minute revision. Starting with the CPU. So the CPU is our central processing unit. We have one CPU in a computer. Its job is to carry out program instructions, and the instructions are done using data. We've got this clear distinction between instructions and data. The instructions are what to do, and they are applied to bits of data. Now inside our CPU, we have other components which you've got to know about. Starting with the ALU, the arithmetic logic unit. What it does is carry out the maths and also logic, like Boolean logic, needed to carry out those instructions. The control unit really runs the show, so it coordinates the fetch execute cycle, and also within that it will decode instructions. Cache is a type of memory which is really small, so we're talking only megabytes usually at max, but it's really fast. And what cache does is hold frequently accessed items. Those could be instructions, could be data, and it could be addresses as well, things which are needed really often. And cache is checked before the CPU will check RAM. Now if cache is small and fast, the registers are ultra small and ultra fast. I tend to think of them as being sort of where the workings out of the CPU goes. And there are four specific special purpose registers you've got to be aware of. The first is our memory address register. This is an address, so where we're looking for in memory, and it's quite a general address. It's basically whatever you're doing. It's the address of where you're fetching something from, so where in memory, or if you're about to write it to memory, where you're going to write it to. The MDR is really the counterpart to this because it will store the actual thing the MAR is pointing towards. So either the instruction or data that has just been fetched or will be written to momentarily. The program counter is another address register. This time is the address of the next instruction to be fetched from memory. And finally, the accumulator just holds the results, so data, from ALU calculations. And the term von Neumann architecture is quite a vague one, admittedly, but essentially von Neumann architecture is built on these components. And this structure of a CPU carries out, as I mentioned already, a fetch execute cycle. Really, there are three stages to this. In essence, during fetch, you get an instruction from memory using the address given in the program counter. Once it arrives in the MDR, the program counter will change to be the next instruction's address, ready for the next cycle. In decode, the control unit will decode the instruction, meaning it interprets it, it figures out what to do next. Because in execute, it would actually have to carry out this instruction, usually done by the ALU. Most of the time it will need some additional data, so data is not fetched during fetch, confusingly it's during execute, and results may all get written back to memory at the end of this cycle, and this will repeat many times a second. How often this repeats a second is based on the clock speed of your CPU. So this is the rate at which your fetch execute cycle is carried out. Now for most CPUs, the rate of this is in terms of gigahertz, so billions of cycles per second. If you increase the clock speed, the CPU will work harder and do more of these cycles per second. The number of cores is another important characteristic. Essentially, if you've got more than one core, they're really a mini processor inside the CPU. So multiple cores, if your software allows it, will mean each core is able to do its own cycle at the same time, meaning instructions can be executed at the same time in your CPU. Cache size is another factor. If you've got a bigger cache, you can store more regularly used items, which means you've got less reliance on the slower RAM. It also speeds things up. So if you increase any of these three things, either together or individually, it will increase performance. And one final small thing in this topic, literally, are embedded systems, which are computers held inside other devices, thinking household appliances, thinking cars. They're usually very simple and have one purpose only. They do something very specific related to that device. We've got two types of storage in a computer, primary and secondary. Primary storage consists of RAM and ROM. Cache and registers aren't usually primary storage because they're part of your CPU. But RAM and ROM are both directly connected to the CPU and they're separate from it. I want to start with secondary storage. This is where the vast majority of your programs and data are stored. It's non-volatile and it's kept for long term. Non-volatile means when power is turned off, the contents stay. Whereas RAM is volatile, which means as soon as you turn off your computer, all of your open programs and data get deleted from RAM. So they're copied from storage into RAM as soon as you open them. Now, when RAM is full, sometimes the operating system will use part of secondary storage as something called virtual memory, where it acts as if it is an extension of your RAM. Now, secondary storage is much slower than RAM, and so if you have to use virtual memory, it will slow down your computer. Now, compared to RAM and storage, ROM is very unimportant most of the time, but it is non-volatile. Its one important job is right when you start up your computer. It contains the program which runs as soon as you boot up your computer. So you press the on button, the program in ROM gets run. And this program's main job is to load the operating system, which is stored in secondary storage, into RAM. Once the OS is in RAM, the other programs can get loaded into RAM, and ROM is not really used. Now, ROM is read-only memory, which means it can't be changed. RAM stands for random access memory. It can be changed. There are three main types of secondary storage. Magnetic storage, the main example are hard disk drives, HDDs, and they work by having on the disk surface two levels of magnetic polarity. So one represents binary 1, another one represents binary 0. A DVD is an example of optical storage, and instead of using magnets, it uses light and different reflections of light to represent binary 1 and binary 0. Solid state storage includes SSDs, solid state drives, and these are just a big chunk of circuitry, loads of logic gates. Nothing is moving in SSDs, whereas magnetic and optical both have a spinning disk. You need to be able to evaluate these. So magnetic hard drives are very reliable, and they usually come with quite a large capacity, but they break quite easily, they're not very durable, and also the spinning disk produces noise. Optical discs are portable and reliable, but they're very undurable. You can scratch them easily, and per disk the capacity is much lower than, say, a hard disk drive. SSDs are the fastest secondary storage. They're really quick to read and write, and they're also durable because nothing's moving inside, but currently their cost is much higher. When we're storing lots of things in binary, we have different binary units, and you've got to know these terms and memorize the order. So we start with a bit, which is just A0 or A1. 4 bits is a nibble, and in a byte, there are 2 nibbles, and so 1 byte is 8 bits. After this point, the pattern becomes very easy because a kilobyte is 1,000 bytes, and then from then onwards, each term is 1,000 times the previous term. For conversions between binary, hexadecimal, and denary, I would suggest using place value tables, which look like these. Don't have to memorize this because for binary, each column is 2 times the previous one. Hexadecimal is 16 times the previous one, but we will start with 1 on the right hand side. You won't always need every column, so for instance, to convert between 101 to denary, I'd stick it in like this and add up 4 and 1, and so 101 in binary is 5 in denary. Hexadecimal has got 16 digits, and 0 to 9 are the same and mean 0 to 9, but between 10 and 15 you've got letters. Now 10 is A, 15 is F. That's all you've got to learn, then you can work out using the alphabet between. So for example, if I had A1, I'd stick it in the table and do 16 times 10, 160, plus 1 times 1, which is 1. So A1 would be 161 in denary. Binary addition is the exact same as normal addition except for 2 key rules. 1 plus 1 would be 0, carry 1. So you carry a 1 into the next column, going right to left. And 1 plus 1 plus 1, so 3 ones in a column, you'd write down a 1 underneath and carry a 1 to the next column on the left. Binary shifts are just adding or removing digits. A left shift will double the number. So if I did a left shift to 101, it would just become 1010. So I'd stick a 0 on the right hand side. By the way, the left digit is called your most significant bit. The right hand side digit is your least significant bit. So a right shift is halving the number, and you're taking away a digit, you're taking away the least significant digit each time. So the digit on the right hand side gets lost every time you do a right shift. So a right shift of 2 would get rid of this 0 and this 1. So you are halving each time you do it, but ultimately, if you are losing ones as you go, you are rounding the number down. An issue which can occur with both shifts and addition is when you get too big. If your result takes up more storage space than is possible, this is called an overflow error. So if you've got a byte and you're doing addition and you carry beyond the 8th bit, that would result in an overflow error because it can't store that full number, so it stores a wrong version of that number. Let's now go through the 4 other big areas in this topic. So when we are representing characters and binaries, so letters, numbers or symbols, we use character sets, which are just a group of codes for each character. So a binary number allocated to every character. 2 big character sets, ASCII and Unicode. ASCII only has an 8-bit character code, which means there is only room for 256 characters in ASCII. The maths there is 2 to the power of how many bits we have. 2 to the power 8 is 256, which is not enough for other languages apart from English. So Unicode is the latest version, which has room for thousands and thousands of characters. So pretty much every language in the world. This has at least 16 bits per character, but that varies. Now, just one thing to realize is the codes are in order. So the ASCII code for A will be 1 smaller than the ASCII code for B. Images are represented as a series of pixels. A pixel is a block of color, and you don't get any smaller than a pixel. Now, the resolution of an image, in essence, is the number of pixels. So in this little snapshot, we've got 9 pixels, so the resolution is 9. But it could be expressed as width times height, so 3 times 3. The color depth is the number of bits per pixel. It's not how many colors there are in the image. Now, this image has got 4 colors, and so to work out the color depth from this, you've got to sort of work backwards. So you're thinking, well, 2 to the power something equals 4. What is that something? In this case, the missing gap is 2. So the color depth of this image is 2, it gives 4 colors. Along with the actual pixels, metadata has to be stored. This is data about data and includes just essential things which have to be included to recreate the image, but also often some extra details, usually coming from the camera. When I'm speaking, my voice is leaving my mouth as analog sound, but as it enters my microphone, it is converted into digital sound by my computer taking samples of the amplitude, the height of the wave I'm speaking, and this is done at regular time intervals. And the time intervals are dictated by the sample rate, which has the unit hertz. This is the number of samples taken per second. The bit depth, essentially the same idea as the color depth, just for sound, is the number of bits allocated to each sample. Now, for color depth, resolution, sample rate, bit depth, as you increase these, the quality goes up, but so does the file size. So you've got that trade-off. To work out file size for both images and sound, you just multiply the terms together. With sound, you've got to multiply it by the duration as well. Compression reduces file size in order to take up less space and reduce transmission times. Lossy compression will actually delete part of your file, which is really effective, but means a loss of quality. That's not a big deal with images and sound. An alternative is lossless, which just rearranges a file to be more efficient. Now, you have to use lossless on text documents and program files because you can't afford to just be deleting part of it. All of it is really important. Moving on to some network types. So LANs and WANs. A LAN is a local area network over a small area, usually just a building. And a WAN is a wide area network, which is not only over a bigger area, but crucially a WAN has infrastructure, has cabling, hardware, etc., owned by multiple entities. In a client-server network, devices take on one of 2 roles. They're either a client or a server. A client requests something. For example, it might request a website from a web server, and the server responds giving over whatever they've requested. So you've got this central control because the servers really run the show. They decide what to give and who to respond to. In a peer-to-peer network, there is not this central control because all devices can sort of flip between being or acting as a client and a server. So pairs of devices can connect independently. There's no oversight particularly because any device can connect to any other device and share information directly. Topologies are about the arrangement of your network, and there are 2 ones you've got to know about: star and mesh. So a star topology has this central node, this central device, which every other device has to go via. And so as a downside, you're very reliant on this central device because if that central device, like a router for example, goes down, well, you are in big trouble. But the key advantage is it's very easy to add new devices. All you do is add a new device, stick a wire to that central device or connect it up wirelessly, and you're good to go. Whereas in a mesh topology, you've got connections to every other device And so it becomes very, very complicated as it gets bigger and bigger. But because you've got this dedicated path direct to every other device, very high performing. You get very few collisions. The collisions where several devices are trying to communicate at once, and errors occur because they just get mixed up. Now, what the central device can be is a few different types of hardware. So a WAP, or a wireless access point, provides a wireless signal. Often it's plugged into a router or built into a router. A router will forward packets between networks, so it'll take in a message and route it to the correct destination. Every device connected to a network has to have a network interface card to enable you to plug in things like Ethernet cables, which is one type of transmission medium, what you actually communicate through. Now, every NIC, partly where you need it, has got a MAC address built in. A MAC address is a unique address worldwide, specific to hardware, and it enables you to pinpoint the correct device on a network. So if you're sending within one local area network, if you know the MAC address, you can ensure it goes to the correct destination. And device which uses this is a switch. A switch is a bit like a router, but within a single network. It uses the MAC addresses to make sure packets go to the correct destination. Bandwidth is one of the many factors which affect the performance of a network. Bandwidth is the maximum amount of data that can be transferred at any given time. And so, as you add devices to a network, you have to share this limited bandwidth across all of these devices. The more devices you have, the longer it's going to take each individual device to transmit. And also, if you've got more devices transmitting at once, this means collisions are more likely. You get these errors, which have to get resent, slowing things down. A few concepts related to the internet are these, the internet being our global network of networks. Unlike MAC addresses, which tell us nothing about where a device is, an IP address will roughly tell us where the device is geographically, so where in the world it is. There are two types of IP addresses currently used. Version 6 is much, much bigger because version 4, we ran out of combinations. There wasn't enough space for every device in the world. I mentioned the word packet before. Just to be really clear, when we send data over networks, it's split into lots of different packets, and among other stuff, a really important thing to put in the header of a packet is the IP address, so that the router or routers can know where to send those individual packets. Now, IP addresses are a bit of a pain to use, especially version 6 addresses, and so when we look up websites, we don't want to type in the IP address. Instead, we type in the URL, the Uniform Resource Locator, or the domain name, and a system called the Domain Name System will look up the corresponding IP address so we can connect to the website. And lastly, the cloud is where we have resources or files being hosted, as in held, somewhere else, and they can be accessed through the internet. So we've got a bunch of servers which are holding our files or some software, and we access it through the internet. These can be really, really powerful and have very large capacities, for example, and they're flexible because you can access it from anywhere, but you've got to have internet connection, and you are putting a lot of trust in these cloud providers to be secure and to be reliable. The last bit in this topic is all about protocols, which are a set of rules enabling devices to communicate. And protocols are examples of standards. A standard is just an agreed set of rules designed to ensure compatibility across many manufacturers. And we often talk about layers in relation to protocols. A layer is just a grouping of similar protocols. And the point of this is to enable more flexibility, so you can switch out protocols if you want to. As long as it's in the same layer, you can change a protocol and it won't really affect the rest of your communication. Now, the list of protocols is long and filled with acronyms. So if I can just focus on the most important things to remember. So TCP is what splits data into packets. It also handles errors. So when you get collisions, TCP will resend it and make sure it arrives. For the email protocols, POP, IMAP and SMTP, POP and IMAP are alternatives. Both are for emails being received. POP won't have any communication with a mail server, whereas IMAP keeps in contact, it keeps synced up so that changes on your client match changes on the server. And for our wireless and wired protocols at the bottom, well, as a general rule, wired networks, in particular Ethernet networks, tend to be more reliable, have less interference, but they're less flexible, you can't add devices nearly as easily, and the security of wired networks is generally better. Now going through some of the big types of cyber attack, starting with SQL injection. This is where an attacker tries to put in some SQL code into usually a user input form to try and interact with the database behind the scenes. So you might type in code like this, drop tables, which would delete the table. You might try and damage it or try and extract data this way. You control this by validating user input. Brute force attacks are where the attacker tries every combination of something like a password. You can reduce the effect of this by having longer and more complicated passwords, and having a limit on the number of guesses somebody is allowed to make. A denial of service attack, a DOS attack, is where the attacker tries to deny service to legit users by flooding a device, often a server, with lots and lots of network traffic, causing it to crash, meaning nobody else is able to use it. Social engineering attacks target the humans, not the actual computer, and they're trying to gain information or money from the poor person. So phishing is a good example of social engineering. You might get messages, texts or emails which look like they're coming from a trusted source, but actually take you to a link to a fake website. You put in your details and the attacker gains access. Often training and just general awareness are good ways to reduce the risk of this happening to your organisation. Malware is malicious software, so it's a big category. It's not just one particular type. So viruses fall under this category, as do things like spyware. And each type of malware works in different ways, but usually they're trying to either damage your computer system to cause it to slow down or not work properly, or they're trying to extract information from you to use in other attacks. A virus, much like a real-life virus, will spread on your computer into other programs. Well, how can we prevent these? Well, with lots of different techniques, but the ones I think you need to know most are these ones. So penetration testing is where an organisation will often pay somebody else to try and attack their system. Now, it is a simulated attack. It's not going to actually cause any damage, but you're trying to break your system in order to find any issues. So it's where finding these bugs and finding these vulnerabilities in the aim to fix them if a real attack happens. Firewalls are listed very commonly as answers, but are often not very well understood. A firewall is either a bit of hardware or a bit of software which checks ideally all of the packets, both coming into the network and going out of the network. It's ingoing and outgoing. And it's checking them to see if they don't meet a certain rule. So maybe there's a certain IP address which is banned, maybe there is a certain pattern of packets which should be blocked, and so it can block certain packets. They're not banning individual people, it's just looking at individual packets, not wider users, and doesn't even look at the contents of it most of the time. Now, physical security is just blocking off access to a computer, so things like CCTV, locks, actually having staff, nothing on a computer, it's what goes around the actual computer. Anti-malware is blocking different types of malware, so it will scan for malware on your computer and remove it if it finds it. The malware is known because it's got a database of all the malware, which is why updating anti-malware software is especially important. User access levels are all about who can read what, who can write what, to prevent people changing stuff they shouldn't really have access to. So you might have admins who can both read and write every file, but you might have less important users who can only read certain things. It cuts off access to important documents. And encryption is also not very well understood along with firewalls. So encryption is where you scramble data so that only those with a key who are authorized can decrypt the data and understand the text. So you might scramble some text into just complete nonsense. You can still read it. So don't say it's unreadable. You can still read it, you just can't understand it. So encryption does not prevent interception, where somebody just gains access to the packet, but they just can't understand it without that decryption key. The operating system is the software which manages hardware and other programs on the computer. The 5 specific things you've got to be able to know about are these. So starting with the user interface, this is what the user sees on the screen. So all of the menus it will have. The 2 types of user interfaces are GUIs and command line interfaces. So a GUI is a graphical user interface. A command line interface is where you've just got text on a screen, there are no buttons you can click, and so on. And a command line interface is often a little bit more concise and you can do more things with smaller amounts of work, but GUIs are generally easier to use. Regarding memory, we've mentioned already that we need to load programs from secondary storage into primary storage before they're executed. This is controlled by the operating system. So it will decide when to move stuff across, it will decide when to delete stuff from RAM, and when it should get executed. Most operating systems support something called multitasking, where if you've got multiple programs waiting to be executed, what the OS will do is rapidly switch between the one being executed, so it appears like you've got multiple tasks happening at once, whereas in reality it's just they're being rapidly switched between, and that's all managed by the operating system. Peripherals are external devices like headsets, like printers. When you plug these in, most of the time you have drivers being installed. This is managed by the OS. A driver is a small program enabling your computer to communicate with this other device, which is external. The OS uses the driver to communicate with this device. User management relates to the fact that you often are allowed to make several accounts. That partitioning is managed by the OS, as is the password system and so on. And within a user's account, you've got different files. The folder structure, the copy and pasting, the renaming is all managed by the operating system. Now we also have another category of system software, which is utility software. And this is just there to support the general running of your computer system. It's not aimed particularly at users like application software is. This is about keeping things running nice and smoothly. Now, encryption and data compression software are two examples, but defragmentation software requires a little bit of a recap. So this only works on magnetic hard drives. You would not really use it on an SSD because it doesn't have the same weakness, which is where you've got the data stored on the disk affects how fast it is to access. So a disk which is fragmented has got to a point where it's got so full that you've got files which are separated across the disk. So you might have the same program in multiple different locations on the disk, just because there wasn't space to put it in one big go. When they're separated, it slows things down because to access this one file, you've got to go to several different locations. And so defragmentation software is aiming to speed up these often older hard drives by just reorganizing the disk to move programs so they're now as close together as possible. Within the last topic, there are 3 laws you've got to know. Starting with the Data Protection Act, this is all about personal data and the responsibility of organisations to look after it. So our data must be kept secure. There can be big fines if companies don't have adequate security. And if you are collecting data about individuals, you must gain their consent. And as an individual, you have got certain rights. You can see the data collected about you, you can ask for it to be changed or deleted. A second bit of legislation is the Computer Misuse Act, which, in a very, very quick summary, is about hacking and malware. This is the law which makes both of these things illegal. You can't damage a computer system, and you can get prison sentences if you do this. The Copyright Designs and Patents Act is all about intellectual property, so ideas people have, things which are quite easy to steal unless you've got a law like this one. So, for example, for us, that might be a design of hardware, which is more likely to be patented. A patent is a expensive but quite strong legal protection, whereas if you're writing software, that's more likely to be copyright, which is automatic. So essentially this means if you've come up with this idea and it's protected under this law, somebody else wanting to use it or share it will likely need to get permission from you to do so. And this can be informal, but it can also be in the form of a license, which is some agreement on the terms of your use. Now, related to this law, but this is not a separate law, certain software is open source. Now, open source software is usually free. First of all, it's usually free because the source code is publicly available. Somebody can open up the file and see the Python code or the Java code and just see exactly what the code was. And so therefore, if somebody can do that, it's very easy to not pay for it because you can just copy and paste it into your own program. Often the license which comes with this does allow modification, so you're allowed to adapt it to your own needs. Whereas proprietary software is paid for, and so they won't usually show you the code. Now usually these come with quite a strict license, you can't change it, you can't share it. But the flip side is they're often made by quite big companies. You may well be entitled to support or warranty or something along those lines. A separate but related area to legal issues are privacy issues, so the idea that usually we want to minimise the amount of data somebody else knows about us. There's often friction between governments and individuals when it comes to privacy. You could spin this into an ethical issue because an ethical issue is about what is right or wrong, what should somebody be doing. Censorship and mass unemployment and surveillance could be all ethical issues. Cultural issues relate to this as well because this is much more about groups, how particular groups within society are being affected. Are young people affected more, older people, poorer people, etc. And environmental issues are things like recycling, mining of rare materials, etc. Often, but not always, these are assessed in an 8 marker. For the 8 marker, don't bother writing an introduction or a conclusion, that's not important, and your spelling, punctuation and grammar are not assessed directly. You haven't got to write 8 separate points because it's marked on the whole. What you do need though is a balanced answer. So if it's about good and bad stuff, mention both. And try and relate any points to the context it gives you. Don't just write about general things. And while spelling isn't that important, how your points flow together really is important, so try and connect your points. Do a little plan beforehand is my advice. And that's it. Paper 1 in half an hour. Hopefully it was useful. Hope the exam goes really well. Do your best, try every question, and I wish you best of luck.